In this lecture, we will be discussing about different types of pharmaceutical degradation mechanisms. As a part of chemical kinetics, today we will be discussing about what are the different ways by which the pharmaceutical compounds undergo degradation or decomposition. And we being pharmacists, we need to know different methods to encounter or overcome these types of pharmaceutical degradation. First, we need to know what is the importance of knowing different types of pharmaceutical degradations. If we get to know different methods how uh, these pharmaceutical compounds undergo degradation, we being a pharmacist will get to know what are the various methods that can be implemented to improve the stability of the compounds. And now we'll be discussing each method in detail. Let's see what are the different reactions that our pharmaceutical compounds will undergo under different conditions. So based on that, the pharmaceutical degradation or decomposition is classified as hydrolysis, oxidation, photolysis, photolysis also known as photodegradation, isomerization, and epimerization. Oxidation is also known as oxidative degradation. All these mechanisms affects the stability of the drugs in any of the dosage forms. It could be a solid dosage form, liquid dosage form, or semi-solid dosage forms. Now let us see what are the various factors that actually affect the compounds to undergo these kind of reactions, chemical reactions. Let's see in detail one by one. We need to remember that any chemical compound or a drug which is having a particular activity will lose its activity when its chemical structure is lost. So, if a chemical compound undergoes any of the reactions, then the chemical structure will be changed. Hence, the activity will be changed. So, it is always very important to know what kind of reactions will take place according to the chemical structure in presence of a specific agents or factors under the influence of specific factors. Now let us see one by one. The first one here in this pharmaceutical degradation is hydrolysis. The name itself indicates lysis means breakdown in presence of water. So any chemical compound in presence of moisture or aqueous medium, the chemical structure will be lysed or broken down. So the name itself indicates the hydrolysis. It need to have water. So most of the products having water will show this type of degradation, hydrolytic degradation. So let us say what are the different dosage forms that have at least some amount of water. So those chemical or those dosage form include emulsions, suspensions, and solutions. So even if the drugs have small amounts of moisture in the form of water vapor, also it will aid in hydrolytic degradation. So in such case, it is quite obvious that presence of moisture leads to hydrolytic degradation. So how can we prevent our drug to undergo hydrolytic from undergoing hydrolytic degradation? It is by protecting our drug from the moisture. So, hydrolysis takes place in presence of water or moisture, even in small amounts. Now let us see what are the different drugs that can undergo hydrolysis that are prone for hydrolytic degradation. So these are the main classes of drugs. The drugs are the chemical compounds having esters, amides, lactams in their chemical structure. So any chemical compound having ester bond, amide bonds, lactam rings, ring structure in their chemical structure. So all these compounds are prone for hydrolytic degradation. The name itself indicates this reaction is actually catalyzed by the presence of hydrogen ion or even hydroxyl ion. So based on that, this hydrolysis is classified as acid hydrolysis if it is catalyzed by hydrogen ion, and base catalysis if it is supported by hydroxyl ions. So based on the catalyst, this hydrolysis is being classified as acid hydrolysis and base hydrolysis. So the name itself indicates acid and base hydrolysis. Means here acid or base acts as a catalyst. So if we can break this chain, like if we make devoid of acid or base species in the reaction, we can actually prevent this hydrolysis. Now let me put in this way. Hydrolysis is catalyzed by acid or base or both. So if we are able to block this acid or base presence, then we can actually break or block this hydrolytic degradation. Now how can we do this? It can be prevented by addition of buffers or buffered systems. Now let us see, as we all know that the class of drugs that undergo hydrolysis or hydrolytic degradation include esters, amides and lactams. Let us see, the drugs that undergo ester hydrolysis means the drugs which have ester bond, example procaine, tetracaine, atropine, physostigmine and aspirin. These are the drugs which have ester bond in their chemical structure and they are prone for hydrolytic degradation. And let us see the different examples of drugs which undergo amide hydrolysis, means the drugs which have amide in their chemical structure. Dibucaine, ergometrin, chloramphenicol, niacinamide, barbiturates. These are the different drugs that undergo hydrolytic degradation and they come under the category of amide hydrolysis. Now let's see the drugs that undergo ring hydrolysis. The name itself indicates like the chemical structures which have ring in their structure, like they undergo ring cleavage, breakdown of the ring. Example, benzodiazepines, penicillins, cephalosporins. So these are the different drugs that undergo hydrolytic degradation. So based on the part or based on the functional group that undergo hydrolysis, it has been categorized as ester hydrolysis, amide hydrolysis and ring hydrolysis. If the hydrolysis takes place at the ester linkage, It is known as ester hydrolysis. If it takes place at amide, it is known as amide hydrolysis. If it takes place at the ring, means breakdown of the ring or opening of the ring, it is known as ring hydrolysis. Now, let me explain with its chemical structure. So, this is aspirin. It undergoes chemical reaction and forms salicylic acid and acetic acid. So, here the bond gets broken down. The main concept here is when this aspirin is taken inside the body, it undergoes a cleavage or breakdown to form salicylic acid and acetic acid. Do always remember it is that salicylic acid which shows activity. Now this breakdown should occur inside the body. Inside the body, thus a released salicylic acid will have the actual activity. But if this hydrolytic reaction takes place inside the container itself, that is outside the body, because of temperature changes, because of presence of water, what happens? In the container itself, this reaction takes place. And when we consume that product, means the salicylic acid present inside the container itself, that product, when this salicylic acid enters the body, because of enzymatic degradation, enzymatic activity, this salicylic acid will get broken down. It gets broken down. So salicylic acid will no more be a salicylic acid. It will be a derivative, or it will be a byproduct, or it would be a broken down product of a salicylic acid, not a salicylic acid. So this hydrolytic reaction should occur inside the body, not outside the body. So any chemical compound that enters into the body, it undergoes breakdown. And do always remember the drug will show its action as its entity, whole molecule, or its broken down product like salicylic acid. This is one example. So, and the next one is chloramphenicol. This is the structure of chloramphenicol. Now I've just rotated this image just to make sure that you should not get confused with this structure, because in most of the books it'll be in different ways how they depict the chemical structure. So here this is chloramphenicol, a pure chloramphenicol. It has chlorine molecules, like when we see the molecular structure. Now this actually undergoes hydrolytic degradation, and it is this moiety or the portion of the molecules that shows activity. Now we being a pharmacist, we should make sure that this moiety should not undergo degradation. So to avoid such kind of degradation, but this molecule when it is subjected to or when it is exposed to gastric juices, it will undergo degradation. So to avoid such kind of degradation in presence of solvents, in presence of aqueous medium, in presence of gastric medium, this kind of molecule is chemically modified. See, when we see this portion is modified with sodium succinate, succinic acid plus sodium salt to make it a soluble product. So when this moiety or when this molecule is exposed to a degradative atmosphere, It is only this will undergo cleavage. So our this moiety which actually has the activity will remain as such. So there will be no chance of losing the activity. Similarly, another way how we can make or we can protect the therapeutic activity of the molecule is by modifying the chloramphenicol into chloramphenicol palmitate. So this drug or the molecule, when it is taken inside and because of enzymatic degradation, this will be removed and the actual activity will be secured. So here we are actually modifying the molecule where at the place where it is prone for degradative reaction. Whereas that is how we are converting the chloramphenicol pure form to chloramphenicol succinate or chloramphenicol palmitate. Mostly in pharmaceutical formulations, we will be considering chloramphenicol palmitate. Why? Because chloramphenicol palmitate, it actually protects the molecule from being being exposed to hydrolytic degradation, and at the same time when we convert this chloramphenicol to palmitate, we are actually masking the bitter taste of this chloramphenicol. So we are having two advantages of this chloramphenicol. The first advantage is we are actually improving the taste of the molecule, taste of the drug. From we are masking the bitter taste of the drug, and at the same time, even if this is exposed to hydrolytic degradative atmosphere or environment, this will undergo degradation and the actual therapeutic activity of the molecule will be protected. So let me explain with another example. In few books, they have discussed about ampicillin. How can we improve the stability of ampicillin? Ampicillin, as you all know, that it is an antimicrobial agent. It undergoes hydrolytic degradation. So how can we improve or we can protect the stability of ampicillin? By maintaining the pH of the formulation. So scientists have conducted some experiment and has seen over the range of pH 0.8 to 10, ampicillin has shown decomposition. It has undergone hydrolytic degradation and it is influenced by acid base catalysis. In presence of acid, it has decomposed, and even in presence of base, it has undergone decomposition, and it has followed first order kinetics. Means the decomposition is directly proportional to the reactant concentration. But when the pH is maintained at 4.85 in buffered solution, then the stability of this ampicillin is maintained. Maximum stability is seen at pH 4.85 in buffer solution, and at the same time even at pH 5.85 in non-buffered solution, it has shown maximum stability. Means here the pH plays a major role. That is always important for a pharmacist to actually maintain the pH of the formulation, because it can actually ionize or make the drug to remain unionized in the particular pH range. And even the presence of the acid species can actually catalyze this degradation process. Sometimes even presence of base also catalyze or speeds up this degradation process. So it is always very important for the pharmacist to make a note of the pH of the formulation to be maintained. And also presence of carbohydrates plays a major role, like sucrose. As you all know, sucrose, like when it is solubilized, it actually produces a little acidic nature, though it is actually, say, a neutral molecule, but it has some acidic effect. So hence the presence of sucrose also plays a major role, and it actually increases the degradation rate. Now, why did we speak about sucrose here? Because we are speaking about the acid and base catalysis, effect of acid presence or effect of base presence. Why? Why is it necessary to speak about the sucrose here? Why? Because ampicillin is a very good example for dry syrup, because most of the drugs or chemical compounds that are prone to hydrolytic degradation, they are not formulated as solutions. Instead, they are formulated as a dried powder form, like dry syrups. Now, let's see what are dry syrups. Dry syrups are a kind of formulations where the drugs along with the excipients, the formulation or dosage form in which the drug along with its excipients are present in dry powdered and fluffy mass, which is easily solubilized when added with suitable solvent, mostly purified and sterilized water. So most of the drugs which are prone to hydrolytic degradation, they are formulated as dried mass of powder. Now here the powder mass will be lyophilized, freeze dried, and that kind of powder is actually packed inside a bottle, and it is actually dispensed with the, let me show you. So we are discussing about the dry syrups, and um, so if this is a bottle, okay, now in this we will be having a dried mass, which is lyophilized, freeze dried, a fluffy mass of drug along with the excipients and coloring agents, preservatives, all that stuff. Now this is actually given with another bottle of sterilized water, or even some are packed with the syrup, plain syrup. But here plain syrup, we are not using plain syrup because the this dried mass itself has sucrose in it as a sweetening agent. Now this is packed inside a carton box. So when a patient opens it, so he'll be opening this bottle of, or the pack of sterile water. He'll be adding this into this, and the patient will be, or the consumer will be shaking up the bottle, and this, as it is a lyophilized mass, it gets easily distributed and dissolved, and thus we get a syrup. So that is how we are actually protecting this drug from undergoing hydrolytic degradation. If in case if we formulate this drug directly as a syrup. So during its storage, it will undergo hydrolytic degradation. But here, we are not allowing the drug to undergo hydrolytic degradation. As soon as we add this solvent, we are consuming this dosage form. So we are not actually giving the time for the drug to undergo hydrolytic degradation outside the body. This is how we, being a pharmacist, we need to understand the degradative mechanism, and that is how we need to actually modify the formulation or modify the packaging conditions. And that is why we are speaking about the sucrose, because sucrose, you know, as it is in the dried form, it will not actually affect the degradation rate or the reaction because it is in dried form. As soon as you add, then we need to consume it within the given time. So this is about the hydrolytic degradation, and that is how the method we take up to avoid hydrolytic degradation, especially ampicillin. This is a good example for dry syrup, which is used for pediatric purpose. And next we will be discussing about the concept of prodrug. Prodrug. What is a prodrug? The name itself indicates pro-drug, means it is not a true drug. It is a modified drug molecule which is in inactive form. Now this inactive form, it undergoes activation inside the body and produces the drug molecule. And this is the molecule which will be having therapeutic activity, and this will not be having any therapeutic activity. Now this concept of reducing or modifying the drug into prodrug is to protect the drug or to improve the organoleptic characters. Now by prodrug concept, prodrug helps to protect the drug molecule from undergoing degradation and to improve the organoleptic characteristics of drug molecule. This is actually an important concept. So we are actually modifying the drug molecule. So when this prodrug undergoes enzymatic activation or enzymatic degradation, this product will get broken down into two entities. The one would be the actual drug which has therapeutic activity. Most of the drugs, antibiotics especially, and most of the drugs that undergo gastric juice degradation because of the gastric juice, they are actually modified. Let us see few examples. First one is erythromycin antibiotic. It actually undergoes degradation in the stomach. So how can we actually improve or protect this erythromycin from getting exposed to intestinal tract juices? We will be converting that erythromycin into an ester form at the secondary position. So we are actually inactivating the drug molecule. We are actually disguising the molecule. When it enters into the body, it gets broken down and the active part will be released. If we don't do that, the drug molecule as such will undergo or get exposed to the juices, gastric juices. So this concept is known as prodrugs. So let us say this one. This is the actual erythromycin moiety molecule, and this is erythromycin stearate. The same molecule will remain like that, but here we'll be making use of stearic acid. Okay, So it is known as erythromycin stearate. When this is exposed to gastric juices, now this gets broken down. So this is how erythromycin will be protected. If not, this erythromycin will undergo degradation and the actual chemical structure will be destructed or destroyed. That is how we are actually protecting the molecule from being degraded. This is the concept of prodrug. Even the chloramphenicol palmitate also comes under this category. There are many other examples which come under this prodrug concept. Even sometimes aspirin also, because it is the acetyl, it is the salicylic acid which has activity, right? So it is not the acetyl salicylic acid. Acetyl salicylic acid, it is a prodrug of salicylic acid, undergoes hydrolytic degradation inside the body and gives salicylic acid, which actually have the anti-inflammatory effect. Now, we being a pharmacist, we need to know what are the various methods to protect the molecule from being hydrolyzed. So let us see one by one. The first one is solid dosage forms like capsules, tablets, granules, and powders. Now, how can we protect? By a good by selecting a good packaging materials which are moisture resistant. So by making use of moisture resistant packs, strip packs, and again by storing in the controlled humidity and temperature conditions. There are few containers which have a different closure systems, like different type of lids which actually protect the contents from the atmospheric moisture. And again there are few dosage forms or carton boxes in which we'll be having silica gel bags. Now actually these gel bags will absorb excess moisture present in the surrounding environment. Now let us discuss about the liquid dosage forms like solutions, suspensions, and emulsions. How can we protect? By maintaining optimum pH, by suitable buffering agents, so that there should not be having any excess acids or any excess base which can catalyze this degradative mechanism. And again, by means of different solvent systems, a suitable solvent system of particular dielectric constant. And again, as hydrolytic degradation mostly takes place in the presence of moisture or water, we can actually replace this water by many other non-aqueous solvents based on the drug compatibility, like alcohol in little amounts of hydroalcoholic solutions. Like we can replace some amount of water with alcohol, glycerin, propylene glycol, like that, by replacing the aqueous portions with the non-aqueous portion. So these are the different methods by which we can improve the stability and we can protect the drug molecule from being hydrolyzed. And again, these are the few examples of drugs that undergo hydrolysis and the various methods how we can protect these molecules. The first one is benzocaine, procaine. These are anesthetic agents and these actually undergo hydrolysis. To these drugs we will be adding some complexing agents like caffeine. So because of this complex, for example, let me explain like this. Suppose this is a benzocaine molecule. This, when it is given as such, it undergoes hydrolytic degradation. But when this is complexed with caffeine or any other complexing agents, a suitable complexing agents, so it forms as a complex, right? a network. Now, when this is exposed to such kind of environment, this complex will act as a protective shield and thus protects the benzocaine or procaine from being hydrolyzed. So, use of complexing agents. And again, we can make use of surfactants also. The same concept. Surfactants, it will form, so suppose this is the benzocaine, surfactants, a suitable surfactant, it will form a missile around this. So now this missile will be having two advantages. It will actually improve the solubility and at the same time it will be protecting the molecule from being hydrolyzed. And the next one is in the form of dry powder. We actually discussed about ampicillin, that is for oral use, and also we will be discussing about the drugs for parenteral use. Most of the injections, if we observe, the drugs products will be in the form of fine powder, lyophilized powder, freeze dried powder in vials. So, and this will be when we add sterile water for injection inside, and when we shake it we can actually take back this drug solution and inject into the patient's body. And that is how we are actually protecting this drug from being hydrolyzed, because it is being produced in dry form. There is no chance of uh, in getting in touch with any kind of moisture or the aqueous solvents. So most of the drugs that are unstable in the presence of water, they are formulated as dry syrups, dry powder injections, or dispersible tablets. So there are many vitamins that are available in the market now for these as dispersible tablets. Those tablets, when we dissolve in the water, we need to have it immediately. That is how we are protecting the drug from being hydrolyzed, from being in contact with the solvent for a longer time. And also refrigeration of the drugs. There are few drugs that are to be refrigerated to retard hydrolytic reactions. As we all know, temperature will catalyze any reaction to happen, most of the reactions to happen. So if we refrigerate, or if we store the drugs in at lower temperatures, we are actually retarding this reaction to occur. So that is how we can actually protect the drug from being hydrolyzed. Now let us see the another factor, another mode of degradation. The first one we discussed is hydrolysis. Second one is oxidation, also known as oxidative degradation. The name itself indicates the drug species or the chemical species, it will undergo degradation in presence of oxygen when it is exposed to atmospheric oxygen. So as we all know, to avoid this we need to add antioxidants, also known as antioxidants. Now let us see what are the different drugs that undergo this kind of degradation or this kind of decomposition, like ascorbic acid, morphine, epinephrine, heparin, paraldehyde, tetracyclines, most like the vitamins A, D, and K, like the all soluble vitamins, and most of the lipophilic drugs, they are prone to oxidative decomposition or the degradation. Now, what is meant by oxidation? As we all know, it could be either addition of oxygen or the removal of hydrogen. Most of the pharmaceutical compounds, they are prone to oxidative degradation, and we being a pharmacist, we need to actually protect the molecular integrity of these drugs. Now let us see how can we protect the drugs from undergoing this kind of degradation. And for this kind of degradation, the presence of heavy metals plays a major role. As we all know, most of the heavy metals, they actually act as catalyst for these kind of reactions. And also, there are few solvents which actually speeds up this kind of degradation. Some solvents. And presence of heat and light will speeds up this reaction to occur. So by knowing the various factors which actually speeds up this kind of degradation, we'll get to know how can we protect our product. Now let us see what actually happens during the oxidative degradation. Why is it really necessary to know the molecular concept? Yes, if we get to know what actually happens, we can actually easily encounter this kind of problem. So what actually happens? Let us see. Let me explain this way. For example, if this is the drug molecule, and when this is exposed to atmospheric oxygen directly, it undergoes oxidation. Oxidized product of the drug will be formed. This will be not having any effect. We might have seen or observed few products turning their color, like most of the compounds having iron in their chemical structure, they'll undergo a color change because the iron present in the particular state will get oxidized and the state of the iron gets changed from ferric to ferrous, right? Or the ferrous to ferric. There will be some change in the electronic level, at the electron level, right? Electron number of electron level. So that is how the nature of the compound or the chemical changes. Now what actually happens? This is the thing. Now, how do our antioxidant plays a major role? The name itself indicates antioxidant. Now let me explain this way. Now the same drug molecule in presence of oxygen and in presence of antioxidant, suppose if the drug is mixed with antioxidant, and when this molecule is exposed to atmospheric oxygen, this oxygen will attack the antioxidant, not the drug. Okay, the drug will be remained as such, and this antioxidant will pair up with the atmospheric oxygen, thus protecting the drug molecule. When we look keenly, this antioxidant acts as a competitive agent. So instead of this drug, this drug and antioxidant will share the same or the less kind of molecular structure, and this acts as a competitive agent, pulling back the drug molecule from being oxidized, and this takes the first place to undergo oxidation. It's like sacrificing itself. So this is how an antioxidant actually acts. It actually uh, takes the first place to get readily attacked by this atmospheric oxygen, and it forms uh, you know see this forming the react with the free radicals or the atmospheric oxygen, the free radicals of this atmospheric oxygen. If not, only this will be exposed to the free radicals or the atmospheric oxygen, and thus this oxidative degradation takes place and this chain will be propagated. So if we add antioxidant, this chain propagation will be inhibited. It terminates the chain propagation reaction by forming a stable product. See, the antioxidant will form a stable bond with the free radicals. That is how we are actually blocking the reaction to occur. Now, how can we protect the drug molecule from being oxidized? As we all know, by use of antioxidants. By use of antioxidants. So if we see the definition, it will be really much helpful for us to know how it acts. So antioxidant is a substance which has a lower oxidation potential than the drug and undergo preferential oxidation. Means it takes the first position. It is like a competition between the antioxidant and the drug molecule. So antioxidant will always take first place to undergo oxidation. So until all the oxygen in the atmosphere, or the exposed atmosphere will be consumed by this antioxidant and thus protecting the drug molecule. So even based on this, the antioxidants are classified as water soluble and oil soluble. So based on the nature of this antioxidant and the nature of the drug molecule, we can actually choose. If the drugs of our choice are water soluble, we can choose water soluble antioxidant. Like water soluble antioxidant are especially used are sodium sulfite, sodium metabisulfite, ascorbic acid, sodium thiosulfate. Make sure to remember it is sodium sulfite. Sulfate is different, sulfite is different, sulfide different. So all ites and eights, they differ in their number of electrons. So it is always necessary to know the compound correctly. Sodium sulfite, sodium metabisulfite, ascorbic acid, sodium thiosulfate. Sodium thiosulfate is antioxidant majorly used for parenteral products, based on the drug also. And ascorbic acid, sodium metabisulfite are the commonly used antioxidants. And the oil soluble antioxidant, which actually prevents the chain propagation reaction, include tocopherols, ascorbyl palmitate. See, ascorbic acid is water soluble, ascorbyl palmitate is oil soluble because it is conjugated with palmitic acid. Hydroquinone, propyl gallate, BHA, beta-lylated hydroxyanisole, beta-lylated hydroxytoluene. So these are the antioxidants which are oil soluble that are used in combination with oil soluble drugs. And again, the first one is use of antioxidant. So how can we is use of antioxidants, use of synergist. Synergist is an agent which actually enhances the reaction. The effectiveness of the antioxidant can be increased by the use of synergist. Synergist, the name itself indicates, it shows a parallel action, the same action. So most of the synergist will include the chelating agents or complexing agents. Few say it as chelating agents, few say it as chelating agents. Chelating agents are nothing but the complexing agents, like previously we discussed about caffeine. So apart from that, we have so many chelating agents that are used pharmaceutically. First one is EDTA, citric acid, tartaric acid. So these are actually added to the formulation because if by chance if there are any heavy metals present, these agents will complex the heavy metals and thus the oxidative reaction will be decreased because heavy metals actually catalyze the oxidative degradation, right? So if we complex these heavy metals, we are not actually catalyzing the oxidative degradation. That is how we are actually protecting the drug from being degraded. And the next option is optimum pH. So by maintaining the optimum pH, as we all know. And the most important point is by replacing the atmospheric oxygen. Uh, uh, Let me explain like this. We might have seen most of the vials for parenteral use, a powder form, and here this gap will be actually filled with some inert gas like nitrogen or any inert gas, a suitable inert gas. So if we are actually taking out the oxygen by vacuum and filling with some inert gas, we are actually preventing the oxidation, right? We are actually protecting this drug from being oxidized. So replacement of air by any inert gas will actually improve or protect the drug. Similarly, if we see in most of our vegetable markets, packed vegetable, um, if we see the packed vegetables, here in the pack, the air will be replaced by some inert gas. That is how we are actually protecting the vegetable. So even for few longer days also, the vegetables will have their own color. The color will not be changed because there is no more oxygen inside the pack. It's being replaced. And do not write this as an example in your examination when it is asked. Kindly quote pharmaceutically related examples. And the next way how we can prevent the oxidation is by molecular change, molecular structural change. Like most of the fats or the oils, when it is exposed to air for longer time, there will be some change in its color. We might have seen in the color change of the butter, cheese, or few of the oils, right? So how can we avoid this oxidation? By actually hydrogenating those oils. That is why we'll get hydrogenated oil, the vegetable ghee. So when those type of substances, when they are exposed, they'll not get spoiled so quickly. And next one is protection from light. And coming to this oxidation of oils, this concept is mostly used for oil soluble vitamins. And next one is protection from light. So like amber colored containers, like means brown colored containers. We'll get to discuss about this kind of packaging further in the coming slides. So when we pack the drug substances in such kind of containers, we will be actually protecting from light, because the light and temperature actually acts as a catalyst for a reaction to occur. So if we protect our drug from such kind of factors, we are actually retarding the degradative processes to occur. Now, so this is one of the classic example given in some of the journals or some of the textbooks. Example, epinephrine, it is a drug. So this actually drug will undergo oxidative degradation. But when we add antioxidants like ascorbic acid, we can protect the drug from being degraded. The antioxidants are also known as redox stabilizers. Why? Because redox means reduction, oxidation, loss of, a loss or addition of electrons or hydrogens is nothing but the oxidation, right? And also the most classic example of antioxidant pharmaceutical antioxidant is sodium metabisulfite. It prevents the discoloration. And also by replacing the air with the nitrogen, we can actually protect the epinephrine from being oxidized. So epinephrine is actually produced as a fine drug powder form in a vial for parenteral use. So that is how we can protect a drug from being undergoing oxidative degradation. One is by addition of the antioxidant, use of synergists, and by maintaining the optimum pH, and by replacing the air with inert gas like nitrogen. And the third way by which our drug undergoes degradation is photolysis, also known as photodegradation. This is interesting. Why? Because when a drug or chemical compound is exposed to light, sunlight of particular frequency, it undergoes degradation. Let us see how. Because most of light energy activates molecule to undergo reaction. So most of the chemical compounds, they actually undergo photolysis, photolytic degradation. So how can we protect, we being a pharmacist, we can protect a molecule from being from getting degraded by light energy. Now how actually this light energy acts? Light energy actually activates the molecule to undergo a reaction. So whereas most of the molecules, they absorb temperature, undergo reaction. They absorb temperature and get into the activation state to undergo reaction. There are few molecules, they just absorb light energy and they attain activation energy to undergo a reaction. So that is how. Now what actually happens during a photodegradation or photolytic degradation? On exposure to light, oxidation or reduction occurs. Or even if our drug has some ring structure, the disruption of ring will be seen, or there will be some modification in the ring, or even for few chemicals, if they are present as separate entities, because of this exposure to light, they form chains between the drug molecules and result in polymers. It might cause polymerization also. So the entire concept of a drug will be changed, because our drug has to be a single moiety, but here will be existing it in a chain, as a chain. This will have a different activity. So that is actually important for us to protect the drug molecule from being exposed to the light energy. So after it absorbs light energy, it undergoes activation and it causes a reaction to occur. And during this process, the heat of the reaction will be produced. So it is accompanied by a thermal reaction. Means during this reaction, heat will be produced. So because here we are having two activation factors, the light energy and also the heat that is produced during this process. So it now becomes a chain reaction. It is actually absorbing the light and the heat from the reaction itself. So this photolytic degradation is actually classified as a stage wise, like a second order reaction, first order reaction, and zero order reaction. At last it is zero order reaction, but because it does not uh, depend upon the concentration of the reactants, it now becomes a chain process. Now let us see what are the different drugs that undergo photodegradation. Most of the vitamins, they undergo this photodegradation, like ascorbic acid. That is why on the label, we being a pharmacist, we actually plays a major role in designing a label also, in giving cautions, in writing the warnings to the patient, in writing how, the methods, the way how to consume the product plays a role. So it is always very important for us to actually go through the label, and we need to redesign the label accordingly. So if it is of, if the drug is prone to photo degradation, we need to make sure that the label includes a caution saying protect from sunlight, put in the refrigerator, should be always under refrigerated conditions, like that, stored in a dry and cool place. Why? Because why dry and cool place? Because if it is of moisture, it can catch moisture and undergo hydrolytic reactions, degradation. That is how. So let's get into the point. These are the different drugs that undergo photodegradation: the ascorbic acid, riboflavin, cyanocobalamin, folic acid. So most of the vitamins, hydrocortisone, like steroidal type of drugs like hydrocortisone, prednisolone, and few of um, antibiotics like adriamycin, and anti-diuretic medications like furosemide, next minadione, nifedipine, sulfacetamide is another antimicrobial agent, theophylline is a bronchodilator. So there are wide classifications of drug that actually undergo photodegradation. That is why we need to actually make sure give give good storage conditions to the patient. Now let us see an example. Say vitamin D. So as we all know, we might be hearing if we roam in the sunlight, we'll get vitamin D from the sunlight, but not actually vitamin D. Vitamin D will be produced inside the body. White sunlight will just act as a, you know, catalyst, truly speaking. This ergosterol present inside the body, when it is exposed to sunlight, this is the sun. So vitamin D will be produced inside the body. It is not from exactly from the sunlight we'll be getting the vitamin D. Not. It's not like that. So it actually acts like a catalyst. This is a precursor. This act like a catalyst, and vitamin D will be produced. And there is another effect where actually food, you know, ascorbic acid, it undergoes photodegradation directly when it is exposed. So when we add, DL-methionine, this activity will be enhanced. DL means a form, dextro rotary form and leval rotary form. D form, L form. We might have come across this in our chemistry, D form and L form. Now DL is the equal mixtures of D form and L form. And also at the same time, sulfathiazole sodium is our drug solution. When we add uric acid, it produces a photoprotective effect in buffered and both in unbuffered solution. Similarly, when we look onto the labels, when we look onto the colored drug products, especially colored, tablets or capsules or granules, colored syrups, how will we get this color effect? By addition of approved colors, like FD and C approved means food, drugs and cosmetics approved drugs. For approved drugs or approved coloring agents, approved cosmetic coloring agents, The coloring agents are different for topical purpose and also for internal purpose. So most of the colors, they are given codes, like say for example for red number 3. So when see such kind of coloring agents, when they are exposed to the sunlight or the UV light of particular wavelength, say for a longer wavelength or shorter wavelength, there will be change in its color. The dark red turns out to be a pale red sometimes because of the instability. Now in such cases, if we add dimethyl sulfoxide, this change of the color will be not seen because this has protective activity, photoprotective activity on this coloring. So to produce a stable product, it is not just the drug or the excipients. We need to actually make sure it should have proper preservatives, proper pH, and also stabilizers like antioxidants. And if the drug is photosensitive, we need to add photoprotective agents like that. And also, one experiment has shown that fluorescent light has more detrimental effect than UV light. Though most of the drugs, they undergo degradation under UV, but then even the fluorescent light also plays a major role in having more degrading activity. Now let us say, we being a pharmacist, we actually need to know how can we protect the drug from photodegradation. Photodegradation, the name itself indicates, in the presence of light energy, the drug undergoes degradation. So we should make sure that the product should be stored in the dark, the dry, cool place. And also, this is known as amber colored container. So most of the drugs, when they are photosensitive, they are to be stored in such kind of container. It could be ampule, it could be a smaller container, or it could be a big size container also. It should make sure that it should be in amber colored glasses. And also, packaging in cartons plays a major role. It actually acts as physical barrier. Carton boxes. And also, there are few tablets which are really colored, attractive. Say this is a tablet. So we'll be seeing this as some tablets will be sugar coated, or just few tablets or just simply coated. Now here this coating plays a major role. One is like it will attract the patient, and this film actually uh, mask the bitter taste of the drug. And at the same time, if we include UV absorbers in this film, when this tablet is exposed to light, this UV absorbers actually acts as a filter, and thus protecting the drug from being exposed to the light. So we pharmacists, as a formulation scientist, actually we need to know how to formulate, how to regulate the stability. Now let us see the packaging materials. Now we actually have two kind of packs. The first one is primary pack, second one is secondary pack. Primary pack is the container, is the material which comes in contact with the formulation. Means the bottle, it could be a bottle, or it could be just an vial or ampule. Any container that comes in first contact. First contact means the tablet will be coming in contact with the first container. Now this container will be placed inside the carton box. For example, this is the container, this is the primary container. Because in this we are having drug, this comes in contact with this container, hence this container is known as, this pack is known as primary. Now this bottle is placed in a carton box. Over this we'll be having label, and on this carton also we'll be having instructions on label. Now this is known as secondary pack. Why it is known as secondary pack? Because the drug is not in directly contact with this pack. It is known as secondary. But then the primary pack and the secondary pack plays a major role in giving protection. How secondary pack plays a major role in protecting this drug from photodegradation? Because this acts like a barrier to and this acts like a physical barrier to the light. And the secondary carton boxes will be coming in different variations. In few secondary packs we will be having this kind of filler, though these are the examples that are seen not just in pharmaceutical industry, in most of the industries as secondary packs. But then we'll be selecting, choosing few things which are of pharmaceutical grade. So most of the secondary packs will be having this kind of fillers. This actually absorbs or acts as physical barrier, and in few containers we'll be having bubble wrap. This actually acts like shock absorber. But in most of uh, the drugs that are prone to photodegradation, they have cardboards, like a soft cardboards or a paper roll inside the secondary pack here. So when we see, this is the primary container and this is the drug, this is the label, and this is placed inside a container. This is primary pack, this is secondary pack. So between these also we'll be having some paper roll attached. This actually acts as a physical barrier to the light. So these are the various methods by which we can protect the drug against photodegradation. Now let us see the fourth method or the fourth way of degradation: isomerization and epimerization. So actually isomers are the chemical forms like both have the same chemical structure, but the arrangement of the molecules or arrangement of the functional groups vary. Here when we speak about the arrangement, we need to speak about the spatial arrangement. Variation in spatial arrangement. Now this concept we might have come across in the chemistry, but let me give a basic introduction about this mechanism. For example, this is the drug molecule having functional groups, say functional groups. Now this is the drug molecule which is supposed to have activity. Now because of some reasons there will be a difference in the spatial arrangement. This is the space and this is the arrangement, and because of some reasons the spatial arrangement will be changed, but then the chemical structure will be same. The molecular formula will be same, but then the chemical structure there will be some slight change in its spatial arrangement, that's it. But then the chemical formula will remain same. See, 2Ds, 2Ds, two functional groups, two functional groups, two, I mean like 2OH, 2OH. But then there will be some change in the spatial arrangement. So because of some differences, because of some reactions, because of some factors, So because even in this type of change causes a change in its activity. So conversion of a drug into its optical or geometric isomers is known as isomerization. We are not going deep into this concept. It is not a chemistry class, but let me tell you, explain with some example. So because of this change in its isomers, there will be some loss of therapeutic activity. So we need to consider even this as a factor. So for example, here the pH plays a major role actually. See, here we have taken adrenaline, our drug. Now here at low pH, this gets converted to dextrorotary form. L-adrenaline will be converted to dextro form at low pH. The L form is actually the active form. So L-adrenaline L-adrenaline is actually the active form, but it turns out to be the dextro form at low pH. So this conversion of L form to D form or D form to L form is known as racemization normally. So if we get to know how can we maintain the pH, then this conversion we can avoid. So at low pH, this conversion is seen. So if we get to maintain the pH of the formulation, then this conversion is not seen. The active therapeutic active L form will be as an active form. It will not turn out to be a dextrorotary form, D form. Similarly, epinephrine, the acid catalyzed racemization, is seen in presence of low pH, I mean the same one, the same. And next, pilocarpine, another drug in presence of base or in presence of high pH, this kind of change is seen. So by maintaining the pH, racemization will be controlled. We can avoid it. And let me explain with another example, tetracycline. If tetracycline is stored or formulated in acidic conditions, if the formulation has low pH, the tetracycline will get converted to epitetracycline. Whereas the tetracycline is active form, epitetracycline is inactive form. So why I have given the structure is when we see the same, the molecular formula will not change. The molecular formula will not change. It is only the arrangement of the functional groups will change. The arrangement of functional group will change, so it got its name epimer of tetracycline. And because of the spatial arrangement, change in the spatial arrangement, there will be change in its activity. It becomes less active. The another classic example is vitamin A. Cis form and transform. Not trans, I mean like transform. Okay, now let's see. Because of this change in the pH conditions, this cis trans isomerization takes place. Actually, the cis form will be active form and the trans form will be less active form. There will be conversion if proper pH is not maintained. If we get to see the both molecular or the chemical molecular formula is same. It is only the spatial arrangement will be changed. See, the group will be here, the group will be here. It will be just turned upside down. That's it. So even this transition or change in the spatial arrangement also plays a role. So we should make sure that we should maintain proper pH to avoid this kind of isomerization or epimerization. So these are the various degradation mechanisms that can happen in a chemical reaction. The first one is hydrolytic degradation. Next one is oxidative degradation. Third one is the photolytic degradation. Fourth one is epimerization on the isomerization goes together hand in hand. So we have seen in this lecture what are the various mechanisms of degradation, pharmaceutical degradation examples, and various methods how to overcome these type of degradative mechanisms. Kindly go through the supportive material to this video, and if you have any doubts you can contact me through my mail. Thank you.